Hi, everyone. I have no financial interest to disclose regarding to this presentation. Many people here care about analyzing high-resolution fMRI signals across cortical layer profiles. We usually do so by means of taking reference images with gray matter surface, then to estimate layers, and ultimately extract signals across cortical layers. Unfortunately, this operation is not easy. The segmentation in this example looks okay, but not perfect. The profile is surprisingly flat and blurry. The single line of activity here does not come across as a clear pit here. This is frustrating, given there's a clear narrow peak visible in the activation map. Why is not there in the profile? This is because top-up and alignment never work perfectly. What we want instead are surfaces like this that consider the geometric distortions and reveals a clear peak that we see in the activation map. In this abstract, I want to show how to get it right by means of an efficient acquisition tools that use our proposed protocol with matched distortions. In fact, this registration constraint have been identified as the single most limiting challenge in mesoscopic fMRI at the survey of the brain function study group back in 2018. The layer fMRI literature from the last decade is full of innovative approaches to address such registration issues by means of distortion-matched EPI. However, none of these approaches has ever caught on just yet. Presumably, due to the fact that EPI is noisier, requiring extremely long acquisition time with whole brain coverage and averages. But also, EPI has issue of another dimension, which is EPI phase artifacts. The goal of this abstract is to take this 3D EPI approach to mitigate both issues. Specifically, we want a fast, distortion-matched, whole brain structural reference scan without EPI artifacts. EPI is suffering from two forms of phase inconsistencies: the geometric distortions from B0 inhomogeneities that we want to be in full control of. But even without the distortions, you can still tell that these are EPI, but not flash images. This is because of these kinds of phase inconsistencies that we call fuzzy ripples, which are unrelated to spatial signal misplacement. We aim to take control of both artifacts with the proposed protocol that we call T1234, a T1 weighted scan with 2 inversion times, a 3D EPI, and 4 spatial encoding directions, alternating both the phase and the width polarity. Combine all 4 of these complex value images give us a whole brain images without fuzzy ripples and adjustable distortions. Here, we have the complete sequence diagram of the proposed 3-minute protocol. We use 14 segments to fill K-space. With each segment, we have an inversion recovery cycle to get 62 kc partitions of 2 inversion times. And each shard alternates between reverse width and phase polarity combination, respectively. We developed a block forward model that captured the T1 relaxation across the inversion recovery. and also along the relaxations. The 3D case space is filled with each shot according to Stirnberg's skip typing approach. Across the shot parallels in KC and across the TRs in the diagonal. With this model, we can optimize the gray and white matter contrast across protocol parameters. Specifically, we predict a combination of flip angles that give us the best compromise of signal strength, point spread function, noise propagation, B1 inhomogeneity, to ultimately make the data pushable through the free server. The red dot represents the maximum of this 3D surface. This perimeter search is exemplified here, how we can get good SNR at no contrast, or no SNR with mediocre contrast, or with the right flip angles. We are hitting the sweet spot. This block model can then also be inverted by means of a lookup table to convert the measured signal ratio into quantitative T1 values. With comparable T1 histogram that we would expect it from amplitude range. With this protocol, the data give robust result of automatic tissue type segmentation across the major tools, almost important for layer fMRI. It works out of the box in free server with the quality level that we are used to get from amplitude range. We are also quite happy how stable it is across participants, as seen more than 10 people here, with run-to-run stability TSNRs of 50. Since the 3D EPI acquisition is as fast as 20 seconds per whole brain volume, we can even do fMRI tests during the structural scan. You can grab the second inversion time as T2 star weight bold, while grabbing the unit image for activation-dependent structural analysis. With this, free server reveals an apparent gray matter dilation at the white matter border, small but consistent. Only in visual areas, but not in frontal areas, used here as a control to show the run-to-run stability of this analysis. In conclusion, we developed a T1234 acquisition protocol. This can give us gray matter night amplitude range in just 3 minutes. It has retrospective adjustable geometric distortions that you can match to fMRI, or you can match the distortions during the acquisition. Flipping back and forth between EPI and the structural scan, amplitude range is not so bad and captures the main layer profile. However, in this example, we are lucky that in a small section of the FOV, we have indication of intracortical patterns, like these 2 bumps in deeper layers. With amplitude range, these faint signals are washed out into a prolonged tail. Only with the high spatial accuracy of T1234 surfaces, indications of these deeper blobs are visible in the profiles. I thank you for your attention.